Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you for the Master of Ceremony. Today we would like to continue our speaking, and this time will be led by Professor Dr. Satria Bijaksana from ITB. According to the first, I would like to give maybe short introduction about him. He's a very popular professor. So he got a degree from ITB, and then takes a master degree and a PhD in Canada from Newfoundlands, yeah, since 1992 and 1996, and also he got a lot of publication, hundreds, so I cannot say, which is quite a lot. And then he also got some, maybe now he also one of the list for the rector candidate of ITB. We hope maybe will be the next rector of ITB. Okay, please, time is yours. Yeah.
Okay, thank you, MC. Assalamualaikum warahmatullahi wabarakatuh. Very good morning to you all. And I changed my presentation slightly because I was inspired by discussion with Professor Anton earlier about how to engage these younger generations of scientists with research. So instead of starting up with the presentation, I would take 10 minutes of your time. We'll watch some video, okay? And this probably would inspire the younger generations about international collaboration, especially for girls, women, because there's so many places for women in science. Okay.
This is the first and the biggest research in Southeast Asia that is held in Tomuti Lake, Luwu Timur Regency, South Sulawesi Province, Indonesia. James Russell from Brown University in the United States of America, and his friend Satria Bijaksana from Institut Teknologi Bandung, Indonesia. They are working so hard these past 10 years to prepare this research.
It was back in 2005, so we met personally in San Francisco, this is 2005, meeting, and then we start exchanging emails. And then in 2007, we came to Solana to start some preliminary surveys.
After we did the work in 2007, the first surveys, that was when we both knew that these lakes were going to be drilled eventually. Might take 8 years, might take 2 years, might take 15 years, didn't quite know. But we knew at that point there's really thick sediment in these lakes.
After some surveys and research, James and Satria believe that Nugroho has a record of long history about climate.
So many other lakes don't contain long records like Lake Nugroho. This lake is in fact probably very unique in not just Indonesia, but in Southeast Asia for holding such long, continuous sediment records.
This research project involves more than 40 researchers from many different countries.
So yeah, I'm a palynologist, and so that means that I look at fossil pollen that is contained within the sediments.
I'm working on lakes and lake sediments since 9 years. I've studied different lakes, different climatic settings. So Nugroho is really the first lake I studied in tropical settings. Previous lakes I studied were more in like temperate climate zones or even in Arctic climates.
saya diberikan kesempatan sebagai para saintis, jadi nanti akan terlibat langsung dalam proses pengeboran di Danau Toba nanti.
So I got interested because for me it's a really unique opportunity to come here to visit Indonesia, to be part of such a big project, meet a lot of people, also from the US, from Canada, from Germany, from many different countries.
Jadi terlibat dalam penelitian sudah banyak, namun untuk yang skala internasional seperti ini baru pertama kali.
Saya melihatnya sebagai peneliti dari Indonesia, kita juga ingin banyak orang Indonesia yang terlibat, dan salah caranya adalah transfer ilmu juga dari peneliti-peneliti asing dan saling bekerja sama dalam tataran yang sederajat.
Support comes from everywhere, including from international institutions. James and Satria finally have their dreams come true in the multi-drilling project.
This is a dreams come true. Sesuatu yang telah kita impikan sejak 10 tahun yang lalu. Saya merasa ada sedikit perasaan bangga, cemas, terharu juga bahwa sesuatu yang telah kita rencanakan sejak tahun 2005 masih sebagai wacana, kemudian kita lakukan tahun 2007 dengan survei kecil, kita mulai dengan survei yang lebih besar 2010, kita melakukan workshop internasional tahun 2012, kemudian kita juga harus mengusahakan dapat pendanaan dari berbagai negara, kemudian masalah izin yang cukup panjang, masalah logistik yang sedemikian berat. Terus saya agak sedikit excited, tapi juga ada rasa semacam percaya tidak percaya bahwa sesuatu yang telah yang tadinya kita wacanakan bisa menjadi kenyataan.
Finally starting. We shipped the equipment here in October. The equipment, setting up the shipment, required about 900 emails to set everything up. We've been planning this project and planning how we would do this part of the project, the setup of the rig, for almost 2 years. So it has been an enormous amount of work to get to this point. But now it's extremely exciting that we are finally ready to begin conducting the project.
More than 400 tons of heavy equipment were shipped from the U.S., then being assembled by international drillers.
Roughly 14 containers. 6 of those are modular floating barge units that we connect together to form one large platform. That platform will have dimensions of 8 meters by 25 meters. And then we mount on top of that all of our drilling equipment. So I'm sure you'll have shots of the platform with the drill rig. You're gone away from home for long periods of time. It's hard work. You're working outside in the elements, whatever those elements will be for that day, you've got to deal with them. What we do is with some of our work in the United States, that allows us to try to find out which guys would be best suited to come on these projects. We don't do rotations on these jobs.
There are so many parties involved, like Mining PT Vale Indonesia, that is located near to the research location.
So in terms of if we want to value this, quantify the value, probably it's in the range of $135,000 US.
There are 3 drilling sites that will be the main focus of this drilling project, where in each drilling site there will be various drilling holes. The research team and the drilling team work simultaneously 24 hours a day for 2 months, even though their work didn't go as smooth as it's planned.
set of problems out. Now, after that pump was installed, basically, so the first thing that went really bad is the main pumps that power the entire drilling rig broke. That took 2 weeks to get new pumps and another few days to install. After that, as soon as almost the hour after we got the pump installed, the main hose that's on top of the drilling rig sends fluid down into the lake to clean away the cutting debris. That broke. So that took another day and a half, 2 days to get a replacement hose from Chart. After that, we continued having problems with the mud pump. This is again the water pump, the mud pump. This pumps fluid down into the bottom of the hole to clean out the debris. You can't really drill without it. We also use it actually to build up pressure to shoot the hydraulic piston cores. We really can't core without it. So that kind of problem, and that took a couple days really to resolve itself. But after about, I would guess, maybe 3 weeks or so, we're really not doing anything to shut down. We managed to start drilling again. We got about a week and a half of really good drilling.
Aside from equipment issues, the researchers also faced a protest from the local people.
Kesepakatannya adalah mereka meminta supaya kami bertanggung jawab kalau terjadi sesuatu selama dan sudah terjadinya penelitian ini. Jadi waktu itu Prof Satria Bijaksana menandatangani surat kesepakatan tersebut.
After issues and problems, the researchers finally get what they wanted, the mud, as they planned before.
So, in terms of the overall objectives, not only did we get those 2 primary objectives to build these 2 sites, the different cores from them, but we managed to grow a few cores from the third site. So, yeah, we got everything we wanted.
Because the other thing they found kind of happy is that the researchers scientists have always like this engineering project basically prepare them for international collaborations it's kind of nice. They saw it in because we're looking forward to have these young scientists help us and like scientists.
The mud from the Luti drilling project will be brought to a laboratory in the US to have further research. It will take around 5 years or more to reveal the history from layer to layer of mud.
An analogy I like to use, imagine you're reading a history book. Every time you turn a page, you're learning something new about history. You're going forward in time or backward in time. What we do is we take the sediment core, and you can think about each layer of sediment being like that book. It's telling you something about what the environment, what the history of the lake was like at some point backwards in time.
Mungkin kami bisa cerita mengenai iklim daerah ini sampai 1 juta tahun yang lalu. Itu yang kita harapkan.
We can learn the climate from millions of years ago in this place. That is what we aim at. No matter how long it would take to reveal the secret of climate history that is kept under Toluti, we really can't wait for it. This research will help human beings predict the future through what happened in the past.
Any good? Okay, now let's go to business. Okay. Okay, that project that we did, we drilled the lake in 2015, and now we're still working on the things because there's so many exciting things that come from that lake. One of the issues is about dating, because it's kind of complicated to date 180 meters of sediments. And our previous work with the shallow one, 10 meters of sediment, reflect the age of about 60,000 years. And now we expect that we got all the way to a million or even more, because we passed through the Bruns-Matuyama boundary. But the exact dating is still in progress. Okay, now back to other things. I'm going to talk a bit about the magnetic anisotropy. I know there are a lot of experts in magnetism here, so I'll probably just skip some of the slides or mention only briefly. So actually there are basically different type of magnetic anisotropy, but basically magnetic anisotropy is the barriers between local energy minimum state of the particles. And there are different type of anisotropy at the molecular level, but we will be talking more about this shape anisotropy. Okay, the preliminary or the pioneering works by Graham in 1954 something, they basically inspired a lot of people to use magnetic anisotropy to see to study the rocks textures or petrofabric. And the normal or the most common method that we use is the anisotropy of magnetic susceptibility, or AMS. And over the years, this technique has been modified and expanded, including the anisotropy of magnetic remnants. And it has quite a wide applications in geosciences, from structural geology all the way to paleomagnetism. Okay, so this is the typical size of sample that we're dealing with. So we're not talking about nano size. We're talking about this kind of size. Okay, so the sample is normally, if it's cylindrical, it's about 1 inches in diameter and about 2.2 centimeters in height. If it's cubical, it's about 2 centimeters something. So the overall volume about 8 cc. Okay, so this is the kind of size that we are dealing with. Okay. Okay, so the basic idea is there's a parameter called susceptibility, and in most of the application, susceptibility is considered to be just a simple scalar. This is a ratio between the magnetizations and the field. But in reality, susceptibility is not a simple scalar parameter. It's more like a tensor-like parameter. So this is why it become interesting to study this. Okay? So the susceptibility is no longer a scalar, so we define the susceptibility as a tensor. And in most cases, it's much easier to visually consider the tensor as an ellipsoid like this. Okay? And we have with the eigenvectors and eigenvalues problem, we could resolve this tensor into a maximum axis, a minimum axis, and intermediate axis basically. Okay, there's a number of parameters used to describe the magnetic anisotropy. Okay, and this is the shape anisotropy of selected materials. The red one's actually more like ferromagnetic. Okay. Okay, so this is just a simple diagram showing the importance of some particular minerals to the susceptibility of the whole rock. As you could see, if you have magnetite, even a tiny bit of magnetite, it will basically mask the whole susceptibility of the sample. So typically, some of the rocks would have 0.1% of the magnetite, That this would basically reflect the overall magnetic properties of the rocks. So we're dealing with very, very a few important minerals. Okay, okay, so the idea that when you have sedimentation, that somehow current, for example, would somehow align the particle as they are being deposited, basically give these models that yes, we could basically look at the anisotropy of the sediment as some sort of like indication for the paleocurrent, for example. The same thing also with this is the degrees of the formation of sediments. Okay, and for the igneous rock, the simple idea is that the lava, when they form, it will be flowing, and somehow we believe that the orientation of grains would somehow be oriented along the lava flow, and we expect, you know, that the susceptibility, the anisotropy would somehow also in that direction. Okay? That's the basic premise in the use of magnetic anisotropy in studying sediments and also in igneous rock, for example. Very, very basic thing, but as you can see, this is not as easy as that thing. Okay? So, somehow I have very strong attachment to this topic, magnetic anisotropy, because this is my first exposure to rock magnetism. This is part of my master work and also my PhD work, magnetic anisotropy. At the time, in the early 90s, the idea is one of the question is whether there's thing called inclination shallowing, that the sediments obtained from the all these deep sea drilling project and others in all the ocean would truly reflect the inclination of the field when the sediment deposited, or somehow it's different. The idea is, for example, if you have isotropic sample, then isotropic sample would somehow basically record the field equally, both on horizontal and vertical one. So you end up with the same orientation of remnants or the record in the sediment with the actual field. But the idea is, if you have anisotropic sample, then somehow the record will be skewed. And this thing here is at the time back in the early 90s, it's called inclination shallowing, and this would have grave consequences to how we predict or how we model the motion of plates at the time. Okay, so this is this is my first paper actually, back in 1993. So we basically tried to see whether it is true that magnetic anisotropy is somehow related to inclination shallowing. So we work with some deep sea sediments from the Pacific plate. Okay, and yes, these samples is anisotropic, and also they show that there's some inclination shallowing. Okay, so we put the simple models, and this is basically a mathematical model, and the dots are basically data that we obtained from Kodama and Son. They did this basically laboratory experiments, and we could see that yes, our model fit the data from Kodama and Son. And then we also look at our data. I know some of you are probably more fluent compared to me in terms of statistics. This is messy, but at least we could see there's some sort of alignment. Okay, so we also then work with turbidites. Okay, so this is a much younger sediments. They are still wet instead of hard like the deep sea sediments. So this comes from the offshore of Canada in Prince Edward Island. Okay, so it's much closer to, at the time it was my hometown. My hometown is the island of Newfoundland. On the top, this is the Newfoundland. This is Newfoundland. This is Prince Edward Island. So the core were obtained in this area. Okay, so now we get a better result. Yes, the inclination is somehow related to anisotropy. This is an anisotropy of remanence, and this is the degree of compaction. So there's some correlation. We're happy to see that, and also there's a correlation with magnetic susceptibility. So based on the simple models, we could say, okay, we could predict the true inclination by looking at this distribution. Okay, but that was back in well, more than 20 years ago. Okay, now I put the fast forward button in my life. So now I'm going to talk to the most recent work on magnetic anisotropy in lava. Okay, lava is somehow complicated because there are basically conflicting reports in the literature. Some would say yes, the maximum axis would be parallel to the lava flow. Some are saying no, it was the intermediate axis. Some are saying no, there's no correlation whatsoever between lava flow and magnetic anisotropy. Okay, so we come up with the idea, why don't we test it? And we come up with the idea that maybe there's one missing element in things, because magnetic anisotropy and lava flow, probably we need some sort of like a bridge between the two. So we come up with the idea of what's called the preferred pore orientation. So apart from only measuring the magnetic anisotropy, we use the micro CT scan to look at the actual porosity of rocks. Okay, so we did some work with lava from Ijen volcanic complex in East Java. Okay, so this is the Ijen, and Malang is here somewhere. So it's not too far from where you are now. Okay, so this is the Ijen caldera, and it's much more beautiful with Google. In Google Maps, you could see that this is the rim of the caldera, and this is the famous blue fire, the Ijen volcanic lake, one of the most sulfuric lake in the world, actually. And this is the Mount Raung. I consider Mount Raung is one of the parasitic volcanoes outside the caldera, and this become very common in some of the calderas in Indonesia. So this is what we did with the lava from Ijen. We look at the geochemical properties. We look at some of the parameters. Okay, so we could see that, okay, for instance, the predominant magnetic domains will be a pseudo single domain. The predominant magnetic mineral will be titanomagnetite, etc. Okay, and yes, this sample is somehow anisotropic. Not that great, but still anisotropic. It's only like a 2% or 3% anisotropic. Okay. Okay. So this is the plot. As you could see, the plot is not very convincing. It's still rather scattered. Okay. And this is the result from our micro CT scan. We basically scan the pore of the things, and with a special software, we managed to look at the orientation of the pore space. And this is the orientations on the horizontal plane. And this one here is the orientations in the vertical plane. Okay. Again, this is not very convenient because there's so many axes. Okay. But yet we managed to publish this thing anyway. Okay. That's the important thing at this level. Okay. So the parameter that we look at now is whether there is an angle between anisotropy and the preferred pore orientation. Okay, because now we believe that the preferred pore orientation would somehow be reflecting the actual flow. Okay, so now we try to bridge the anisotropy with the lava flow through this preferred pore orientation. Okay, so this is our result. We published early this year. The student that did most of the work, Fadli Atarita, is now in Queen's University doing a graduate program. Okay. Now, we are not happy with the result in IGEN, so we try to find another a place that we could test our methods. So we moved from beautiful Banyuwangi to Bali, just across the narrow strait of Bali. Okay, and we work with the another caldera in Batur, and this is still we haven't really submitted yet because we still have to work on some of the data and text. So this is still in preparation. So we're doing the same thing, but we use different samples. Okay, so this is the crater of Batur. One important thing about Batur that is make it different with IGEN is Batur is the lava flow in Batur is very well preserved and very well dated, and some of them are very young. Okay, so we deal with the we took the sample from the 1849 eruption, very well preserved. And as you could see, probably if you have a chance to go to Batur, Batur now is considered to be a geopark. It's like it's a protected area, and there's very little vegetation in Batur, so you could see all this lava flow clearly. And that's why we test our methods in Batur. Okay. Okay. Another beautiful place. The students who did this said, this is much better than IGEN because of close to beach and everything. Okay, that's fine. So this is the Batur, the caldera, and again, like any other caldera, big caldera in Indonesia, there's always what I call this the parasitic volcanoes. The parasitic volcanoes just happen to be there's Gunung Abang here, very small one, but then the very famous one here is the Agung. Okay. So this is the thin sections of some of the lava sample that we took. Okay, and this is the magnetic properties of the representative sample from this lava. Okay. Again, you could see that yes, this is more magnetic than lava from IGEN. Okay. But the good thing is they're very well oriented. The anisotropy is very well oriented. This is what makes us happy. Okay, so you could see they're very consistent. You could see there's the declinations of the maximum axis, the minimum axis. They're all well oriented, which is kind of nice. Okay, now this is the result of micro CT scan, and the orientation is much better. The preferred pore orientation in Batur is much better than the one in IGEN. So now we are very hopeful that we could get much better correlation between anisotropy and preferred pore orientation. Okay, so this is the angle between preferred pore orientation and susceptibility axis. Okay, this is the last message for the students. Don't ever give up. Okay, if your professor gives you a difficult subject, take it. If they offer you a difficult project, thesis, take it. Okay? Thank you very much for your attention.
Okay, applause for thank you for very nice talk. And any question? Okay, please.
This one, no, the cost for the project that you show in the yeah, in US dollar or in rupiah.
Or the drilling. Okay, the actual drilling, the cost of equipment, etc., is about $3 million US. Wow. Okay, and that's not include the tickets and everything for the participants or logistics, just for the board. Okay, so we managed to organize this thing here because we got funding. Our the largest sponsor is called the Consortium International Continental Scientific Drilling Program, based in Potsdam now. So basically, this consortium put somewhere between 50-something% of the cost. And then we got some funding from National Science Foundations in the US, also from Swiss Science Foundation, from Germany, Canada, Indonesia. So it's and it took a few years to organize. This is not something that you want to do it now and you could do it tomorrow. It's like I mentioned, it's about 10 years. So from the initial investigation to the actual, because to get that kind of funding, you have to show that you have good result. You have to do a good preliminary result. You have to show, okay, look, this is a prospective place, and then the topic has to be very, very attractive to a lot of people, because the ICE-R3M said this project should be attended by as many scientists as possible, because the samples are very, very expensive to get. This has to be basically used to the maximum with the people from different fields. That's why we have people from different backgrounds working with this project.
Okay, thank you. One question more, ma'am? Okay.
Very simple one. I remember that maybe 20 years ago you taught me about this, about rock magnetism. My question is very simple. Is there any relation from your result between the anisotropy and the rate of flow of the lava itself?
Okay, at this moment we just look at the possible relationship between the preferred pore orientations with the anisotropy. But now I have a master student working on the same lava flow, but at different position, to see whether there's some sort of variation between with time and also with position. And so this person, Billy, he's going to take samples. If this is lava flow, he will take, okay, this sample, but also this sample. Yeah, because there's possibility that there's big differences between the core and the top or the bottom. We're working on it. Cross your fingers. I have to apply for this.
Okay, thank you. Applause again for Professor Satria. Okay, now to